Hi there, everyone. My name's Joe Kimball. I'm a graduate student here in Dr. Grzinski's lab in the Department of Physics and Astronomy, and I'm here to talk about the early detection of diseases. Okay, why? This is a picture of my dad and his first wife, Renee, and two of my half-sisters, Michelle and Danielle. Renee was diagnosed with cancer in the 1980s, and she didn't live longer than a year after being diagnosed. This is a picture of my mom. She was diagnosed with skin cancer 15 years ago, breast cancer 10 years ago, bone cancer 3 years ago, and recently it's going to spread around a little bit more. So it sounds pretty horrible, really, but when you think about it, I actually got an extra 15 years of time with my mom that my sisters didn't get with theirs. One of the reasons for that is that we've gotten better and better at measuring diseases at their earliest stages so we can diagnose them and help get people treatment fast so we can begin to treat it easily and before it turns into a big, big problem. One of the best ways to detect these diseases is to use fluorescence. What is fluorescence? Fluorescence is, as you can kind of see up there, light. It's when we have basically a laser or some sort of light, and it interacts with the molecule, and that molecule will give off light. That molecule we can attach to diseases, to cancer, to Alzheimer's, to proteins, to a wide variety of things, so we can see where it is and how much there is of it. So, while that works, everything's fine. We've been using fluorescence for a while. It's very successful. It doesn't exactly work at the best way that we want it to because of essentially the background. These very small amounts of the beginning stages of diseases, there's not a lot of the disease, so we can't measure it very well. And the problem with it is that actually your body has its own fluorescence that it makes. So if you look up here, you have this is a cell that we're going to add stuff to, but this is the fluorescence that's already producing just naturally. And this is when we then add our fluorophore to it. You can see something there, right? I'd say, yeah, maybe that's a diagnosis, but that's not a very good diagnosis, maybe. We don't like that. We'd like to do better than that. So what's the solution? Here at TCU, basically, we developed a new way to excite those fluorescent molecules, in a sense. So usually what you'll do is you'll have a camera. The best way I can kind of relate it to is playing Where's Waldo? If Where's Waldo is a cancer cell, if Waldo's the cancer cell, or Alzheimer's, or some disease, what's the worst part of playing Where's Waldo? He blends in with the background. It sucks to find him, right? So typically what we'll do is we'll have a camera. It takes a flash, and you have a picture. It takes a picture. But at TCU, what we've determined is that instead, if you have a camera, it takes a flash, and then you go in with a quick succession of flashes, it pulls Waldo right out of the background. So how do we actually do that? We call this multipulse excitation. Typically, we'll come in with a laser pulse. This is the blue line. And the neat thing about these fluorophores is they give off light for not a very long time, for nanoseconds. So a nanosecond is a billionth of a second, okay? So some of these fluorophores have short lifetimes, and the key to it is really that the backgrounds that our own cells have are also very, very short. So you could also have a molecule, a fluorophore, that has a long lifetime, and that gives off light for maybe up to 100 nanoseconds, very comparatively long. So usually you'll come with a laser pulse, it excites it, and we'll measure the intensity of that as a function of time. Then we'll wait for it all to decay out and do it again, bring in another laser pulse at the end of all of it. Now, the tricky part is that we figured out that if instead of waiting for it all to decay, if you come in with a second pulse right after the short one has decayed or your background has decayed, and we're using a long lifetime fluorophore to attach to those cancer cells, we're actually going to pump up our fluorophore over the background. And in that case, we can get orders of magnitudes of sensitivity enhancement for measurements. So the problem is now, unfortunately, that as you can see, these laser pulses are very, very not spaced at all to each other. They're about 3 nanoseconds apart. And to make a laser that's spaced, that gives off light every 3 nanoseconds, I know some people in Germany that could probably do it, but they would charge like $500,000 to buy one of those lasers. So I don't really want to, we don't want to do that. That's way too much money and kind of not worth it in a sense. So what we decided to do was to make us go and play with lasers and optics and glass and mirrors and stuff. So light moves at 1 foot, in 1 foot it moves 1 nanosecond. So essentially what we can do if we have a laser, we just space out with some mirrors and some glass. We just space out each pulse by 3 feet, and you have your 3 nanosecond delay. So we have our 3 nanosecond splitting in between each laser pulse. So this is now going to be actually what we can really do with it. This is detecting cancer-binding sites in rat retinal tissue, and this is with 1 pulse. With 1 pulse, you see absolutely nothing, right? There's nothing really there. But then with 5 pulses, you start to see somewhat of an improvement, and with 20 pulses, you literally have orders of magnitude enhancement in your ability to detect this disease. So that was all done with a $50 instrument that we can be used at virtually any lab across the entire clinical universe across the entire world. For $50, I could probably take any one of you, take in the lab, and build this thing. It takes like an hour. So this could really, really help our ability to have the sensitivity that is unparalleled by anyone else in the entire world for $50. Now, TCU has bought us a new nanosecond camera. This camera takes a picture every nanosecond. So remember, a nanosecond is a billionth of a second. So in 1 second, this thing takes a billion pictures. So what you're going to see is this is happening from 1 to 100 nanoseconds. You can see these dots. This is just a glass slide with some fluorescence on it. And you can literally see the short ones dying out on the far right, and the middle one's a medium-sized one, and the long one's still there. So that's what we're going to be taking advantage of. The short ones go away very quickly, and we can then use our multipulse to even further pump up that long one. But before we do that, we're still at TCU, and this is a fun thing, so we really couldn't help but make, I think, probably the fastest cheer ever for TCU. So I don't know, maybe we can get in the Guinness Book of World Records for that, or just maybe use it for the fastest team as well. So for fastest team, fastest cheer. So it works out pretty good, right? So our real goal of it is, with this new camera and multipulse, is to be able to use it in a live setting, essentially. The other pictures you saw were using microscopes or using something in solution, which is still very useful. But what we'd like to do when you go to the doctor and you get a CAT scan or an MRI or an X-ray, you physically go there and you kind of more or less get into the machine. And they don't have that really for fluorescence. And we'd like to start to develop that here at TCU using this multipulse and this camera. So what it's going to be is when you look in your skin, there could be a disease kind of far in there. And remember, your body is creating its own fluorescence that's basically obscuring our ability to measure anything below it. But with our multipulse, we can essentially get it to come out of there by exciting only our fluorophore and not the background. So what we kind of have is a little model. We took a whole bunch of fluorescence, probably like an inch thick, with a fast lifetime, a short lifetime. And then below it, we filled up a tube with our long lifetime. So it's kind of like a vein underneath your body. Okay? So that's what we're going to be looking for. At the very first part of this, you're going to see a big, bright flash, and that's what you would normally see, like 100% what you would see. Then, as it goes further in time, we're actually able to resolve what we can do with our multipulse. Right now, there's multipulses going on, and you can see that it is the only one existing after 100 nanoseconds. So we'd like to develop this further into actually like a usable diagnostic machine that you could use actually in a hospital or in a lab. So, to summarize, diseases at the earliest stages are really difficult to detect because there's not a whole lot of it. But that is the most important time to begin to detect them so we can start to treat them. And this multipulse technique is a way that we can help for $50 basically at any diagnostic lab across the world that uses fluorescence to increase their sensitivity by orders of magnitude for any of them. Very easy. And then with our new camera and our multipulse, this is going to keep TCU at the forefront of biomedical research for the foreseeable future, for sure, definitely. So, while when you think about it, I know that none of these technologies are really going to help my mom, but I hope that these technologies will help a lot of people out there to help spend not 15 or 20, but maybe 20 or 40 years of time with their loved ones as well. And I think that's a pretty good new hope. Thank you.